Welcome back to the digital training module on the thermodynamics of mixtures. You are inside Unit 1, dedicated to the theoretical foundations of thermodynamics, and you are watching Lesson 2 on the chemical potential. We started Lesson 1 by introducing the concept of equilibrium, which requires the equality of three potentials relating to thermal, mechanical, and chemical equilibrium, and represented by temperature, pressure, and the chemical potential of the components in the mixture. We then moved to explore the consequences of the first and second laws of thermodynamics, and we ended up with 4 different definitions of the energy of a system, each one providing a criterion for chemical equilibrium corresponding to energy minimization, each one appropriate for systems evolving under different conditions. Among the different energy forms, Gibbs energy is particularly relevant to us as it refers to processes which occur at given pressure and temperature, matching our experience as well as the way we perform experiments in the lab. In this lesson, we will connect energies and chemical potentials and see why equality of chemical potentials is a criterion for chemical equilibrium. We start by repeating the reasoning that we have developed so far, this time for a homogeneous open system. Let's understand what that means. So far, we have been concerned with a system that exchanges only energy, both thermal and mechanical, with the surroundings. However, chemical processes involve transfer of mass from a part of a system to another part of the system. For example, from the liquid phase to the gas phase during exsolution of volatiles from a magmatic mass. Therefore, in order to understand the evolution of the energy for each one of the phases that are exchanging mass besides energy, we must account for mass exchange explicitly. And because we are dealing with multi-component systems, we must consider the variation in the mass of each component within each phase. In general, we can express the internal energy for an open system, such as, for example, the liquid phase or the gas phase in an evolving magma, as no more a function of just entropy and volume, as we have seen in Lesson 1 for closed systems, but as a function of also the number of moles of each component in the phase. In fact, now the number of moles of each component is no more a constant, because the components can migrate from one phase to the other in order to achieve equilibrium. By differentiating the expression for the internal energy, we obtain a general expression for the increment du of the internal energy of a phase upon exchange of mass and energy with the surrounding. This is the same as we have seen before, now with the addition of the summation term, which accounts for possible exchange of the components making up the phase. For example, silica, alumina, water, carbon dioxide, and so on. Now, here is what the chemical potential really is. Simply just define the chemical potential of each component in the mixture as the partial derivative of the internal energy with respect to the number of moles of each component at constant entropy, volume, and number of moles of all other components. That is just a definition. Our decision to code such a quantity with a name, in this case, the chemical potential. In physical terms, the chemical potential of a component corresponds, therefore, to the change of the internal energy of a system when system volume and entropy are kept constant and small bits of that component are added or removed from the system. There will be a chemical potential for each one of the components in a mixture, different in general from the chemical potential of any other component. With this definition of chemical potential, we can rewrite the expression for the differential of the internal energy in a more compact way. Here I report the same expression in the previous slides that we have derived for a system that exchanges mass besides energy. Therefore, it is appropriate for an open system. Conversely, a similar expression for the differential of the internal energy that we saw in lesson 1 was appropriate for a system which exchanges energy but not mass, therefore for a closed system. While an isolated system, just to remind it, does not exchange neither mass nor energy with the surroundings. Let's write the general expression for enthalpy that we derived in lesson 1, and after differentiation, let's write it in terms of the differential of the internal energy. We now have two expressions for the differential of the internal energy that we can equate to obtain the differential of enthalpy for an open system. We have therefore obtained the differential of the internal energy of enthalpy for an open system, that is, for a system that is exchanging mass besides energy, like, for example, a phase upon evolution towards equilibrium with other phases surrounding it. We can repeat the same procedure exactly in the same way for each one of the different expressions for the energy of the system and obtain similar expressions for the differential of the Helmholtz energy and the Gibbs energy for open system conditions. If we look at them, each one is exactly the corresponding expression for a closed system with the addition of a term including the chemical potentials, and which is the same for all energy forms. Therefore, the observation above on the chemical potential of each component, that it represents the infinitesimal change of internal energy when small bits of that component are added or subtracted at constant entropy and volume, also holds for all other energy forms. In other words, if we add or subtract vanishing amounts of a component to a mixture, the chemical potential of that component tells us what the differential change in internal energy will be. If the component is added or subtracted at constant entropy and volume, the chemical potential tells us what the change in internal energy will be. If the same process occurs instead at constant entropy and pressure, then the chemical potential tells us what the change in entropy will be, and so far and so on for each one of the different energy forms characterizing our phase that is exchanging components. More relevant to us, the chemical potential of a component corresponds to the infinitesimal change of the Gibbs energy of the system when small bits of that component are added or removed at constant pressure and temperature. Now we start to see why the chemical potential is so central for chemical equilibrium. That's because it immediately relates to changes in the energy of each phase when that phase is exchanging some of its components with other phases. Because the first and second laws tell us that minimization of energy is the criterion for chemical equilibrium, it follows a strict relationship between chemical potential and equilibrium. We'll see it better in a moment. But before that, let's see in some more detail the relationship between chemical potential and Gibbs energy. Here, I'm just reporting the different definitions of chemical potential in terms of different forms of energy. Now, let's recall the definition of partial molar quantity of a component in a mixture, which is given by the derivative of an extensive total quantity, capital X, with respect to the number of moles of that component when pressure, temperature, and the number of moles of all other components in the mixture are kept constant. Thus, by comparing this definition with the expression above for the chemical potential, we see that the chemical potential of a component in a mixture corresponds to the partial molar Gibbs energy of that component in the mixture. Note that the chemical component is not the partial molar enthalpy or partial molar internal energy or partial molar Helmholtz energy, because none of these energy forms are defined in terms of the independent variables pressure and temperature. That happens only for the Gibbs energy. A partial molar quantity is normally indicated as a lowercase letter surmounted by a horizontal bar. So the expression at the bottom left corner says exactly that the chemical potential of a component in a mixture corresponds to its partial molar Gibbs energy, lowercase g with a bar on top. For pure substance, that is, for a substance made of only one component, such as pure water or pure silica and so on, molar quantities and partial molar quantities coincide. Therefore, for a pure component, the chemical potential corresponds to the molar Gibbs energy. Accordingly, the total Gibbs energy of a pure substance is simply the chemical potential times the number of moles of that substance. We are now fully in the position to understand why the chemical potential is an effective criterion for chemical equilibrium. The answer is that the chemical potential relates directly to energy, whereby energy minimization is the criterion for equilibrium. Let's see it more clearly with an example. Assume that we have two multi-component phases, two mixtures, that we call phase A and phase B, placed one beside the other and allowed to evolve towards equilibrium at given pressure and temperature conditions. Consider the behavior of one component, here represented as blue dots. Say that initially the chemical potential, of the component in phase A is greater than the chemical potential of that same component in phase B. We have seen that at constant pressure and temperature, minimization of the Gibbs energy is the criterion for equilibrium. Now, we have seen above that the chemical potential of a component is exactly the measure of how much the Gibbs energy changes when a small amount of that component is gained or lost at constant pressure and temperature. Because the chemical potential of the component in phase A is greater than the chemical potential of the same component in phase B, the negative change of the Gibbs energy of phase A upon loss of that component is larger in magnitude than the positive change of the Gibbs energy of phase B upon gain of the same component. As a result, the overall change in Gibbs energy is negative. Therefore, transfer of the component from A to B corresponds to overall Gibbs energy decrease, thus to approaching equilibrium. After a certain time, after a certain amount of components has been transferred from A to B, the Gibbs energy of the two phases has changed, and so has the partial molar Gibbs energy or chemical potential of the component that has been moving across the phases. In particular, the chemical potential of the component in the two phases A and B now converges to the same value. At this time, any further negative change of the Gibbs energy upon loss of the component from one phase will be exactly compensated by the positive change of the Gibbs energy of the other phase. Transfers in both directions continue, but they are equally likely to occur, therefore, on average, they cancel out. Although at the microscopic level, molecules continue to flow in both directions, macroscopically, nothing is seen to evolve anymore, and chemical equilibrium is achieved. Now everything is clear. Equality of the chemical potential of all components in all phases implies no further chance for a system to further minimize its energy, and that corresponds to thermodynamic equilibrium. We have now achieved our initial objective. Employing exclusively the first and second laws of thermodynamics, we have demonstrated that equality of the chemical potential of all components in all phases is a criterion for chemical equilibrium, in that it corresponds to energy minimization, which in turn corresponds to entropy maximization prescribed by the second law. According to our findings, chemical potentials are normally employed in thermodynamic problems. However, when dealing with equilibria involving fluid systems, such as magmatic melts and their coexisting gas phases, one other quantity is often more conveniently employed to describe chemical equilibrium. That quantity is fugacity. In lesson 3, I will introduce the concept of fugacity and show you that equality of fugacities is a criterion for equilibrium as general as equality of chemical potentials. After that, we will be ready to write a general equation for liquid-gas equilibrium that we will then employ throughout this training module to write a model for magmas. See you in lesson number 3.